Good afternoon, everybody. Welcome to Module 2, which is the introduction to the rheology software with the Kinexus. My name is Philip Rolfe. I'm one of the rheology technical specialists here in the US at NETZSCH, and we'll be talking about some of the features of the software and an introduction to viscometry. So we have the software at 4 o'clock now, and at 5 o'clock we have another module. This will all be recorded if you want to watch later, of course. So let me just get the laser pointer here. So in this module, we're going to go through the Kinexus concept of the software, and then basic test setup, and then the typical measurement procedure. And this is actually a fairly easy to use instrument, so you'll hopefully see that with the training today. So the benefit, the beauty of the Kinexus software is how it does help you with the R-Space software, and it guides you right through the whole running of a test. You can run these template sequences, which are included with the software, and it will help you to be able to run a test without even needing to be a rheometrist. So you don't need to know what you're doing particularly. You don't need a lot of training in rheology, but if you want to, you can also write your own sequences and create these custom solutions. So this can be as complicated as you like, actually. So you can run one of these measurement sequences. They're very easy to do. And as you see on the right-hand side here, we have a sequence. It usually has 3 tabs: properties, live display, and start sequence. And in the start sequence, these are the actual actions. You see the actions that do things. And there's one here that says set full temperature equilibrium. And so that's actually going to tell the instrument to set the temperature and wait for thermal equilibrium. And then we're going to run a viscosity shear rate table afterwards. So that will be for thermal equilibrium and then a viscometry measurement. So you can drag and drop these actions in if you want to create your own sequence, but we also have some predefined ones, which makes it very easy for a new user. Now, when they designed the software, Malver and Panlitical did a survey and asked people what they would like, and the overwhelming response was that people wanted more assistance with doing rheology. They needed to know what test was most appropriate and then how to interpret the results and things like that. So the engineers came up with this kind of design module. So all rheometer systems have had this experiment level in them, where you can choose to do a viscometry test or an oscillation test or a creep test, whatever. And then you'd need to know which geometry to use, what stress or shear rate range, and how many seconds per point, how many points, what how to interpret the results. You know, if the data was going to show good sample behavior or bad sample behavior. And this experiment level is still in the software. So it's not like we took this out, but we also added the solve level. So in the solve level, you can actually just type in a problem, kind of like a Google search. You could type in stability or high shear stability or sedimentation or printing or pipe flow or something like that. And it will list you all of the tests with those keywords in. And then from those tests, you can choose one and just set start, and it will acquire the data. And then you can look at the PDF, which comes with this R solution sequence to see how to interpret the results. So it's a very quick way of getting the test that you want to give you sensible data right away. So these R solution sequences are in our solve level. And these are actually built up with a lot of different actions. So we have these kind of building bricks, if you like. This is the design level, where there's measurement actions, there's analysis actions and sample loading and things like that. And then you can add these in and take them out at will, and then save the sequence with your own name. So these R solution sequences are read-only, but you can edit them and then save them with your own name afterwards. So I often say this is kind of like a battleship. You know, if you had a Lego kit and it was a battleship in here, and you actually said, you know, I want a cruise liner, you can open the sequence, you can take off the gun turrets, and you can get the sunbeds out here and put them on, and then save it with your own name. and you are having a cruise liner right away. So it gets you from 0 to having good results in a very short order. There's actually a few other good modes here in solve level. One is sure. This is diagnostic functions. So if you were to call the help desk and say, I'm not sure if I damaged my instrument, we were moving it, somebody walked into me or whatever, then the help desk would probably ask you to run sure underscore and then 0002 or 003 or whatever part of the instrument they want to check out. And this instrument sequence will run diagnostic checks on it, and it will tell you if everything's fine, or if it's something trivial, we may be able to just recalibrate it over the internet. Or if it's something major, hardware fault or issue like that, then it should identify which parts will be needed. So that's a very quick way of fixing the instrument using sure, and it saves people having to make multiple trips to the customer, and it gets the customer up and running more quickly. Performance is a module which checks the instrument's running to specification. So if you really wanted to see, is it as good as it used to be, or is it deteriorated over time or something like that, then you can run one of these performance tests. And then grade, these are ASTM tests. So if you have asphalt testing and you want to run one of their common AASHTO tests as they're known, then these are all in the grade section. So in the solve level, you can see this a bunch of sequences in the software. Then we have the experiment level, and then the most basic building bricks are the design level. So these are really very versatile, and I think the Kinexus is quite unique in that it has the solution level in it. It's the only rheology software that actually has problem-solving sequences in there and PDFs with example data and interpretation of the data that's been measured, so that you can run those tests very quickly and get what you want. And the sure also for checking functionality of the instrument really helps you be assured that the data is good on your instrument. Okay, so the experiment level obviously has a library of common tests, and you can easily use those if you want to set them up. And these are actually mostly in the toolkit. There's also the design level, as I said. These are kind of basic building bricks. Now, the way to find these things is to use the Finder. So if you look at into the software, there's this Finder button at the top left-hand side of the screen, which actually has the words Finder on it. And when you click on that, it opens this search box, and you can literally just type in the words that you want to search upon. And there are different tabs. So this first tab here shows you everything, and then this second tab just shows you sequences with those names. And then this would be PDFs or application notes with that same name or those words in it, the result file, charts, tables, or report files with those names in. So you can search on any word, you can set a date range, and you can obviously search in different locations on your hard disk drive or on the network. On the front of the instrument, there are some indicators. We kept these to the minimum so that it doesn't become overwhelmingly complicated. But one thing that the instrument really does need to work is an air supply. And if the air is off, then this indicator is white. But when the air is on, this goes green. Now, this is a mechanical switch. It's a little spring on the back. And it doesn't matter if the power is on or off, but basically it will go green if the air is on, if there's an air pressure sensed, or it'd be white if the air pressure's off. And if the air pressure's off, then you really shouldn't be touching the rotor of the instrument because you might damage the air bearing. And we recommend that if you're going to leave the air turned off for some time, that you put this chuck lock on there. This is a thing that clips into the chuck and then holds it basically stationary so it won't rotate. But if you're going to just turn the instrument off and on every day, then you generally don't need this chuck lock. But when you turn on the instrument, check the air is on, and then secondly, you want to check the air regulator. So here's a picture of an older type of air regulator, but the new ones are fairly similar, maybe just more open-looking bowls. And the air comes in on the left-hand side. It should be clean and dry, actually, And the engineer should check that before he installs it, that the air is clean and dry when he installs the instrument. And if it's nominally seems to be clean and dry, what he will do is he'll blow the airline onto a tissue for a minute to see if there's any spits of oil coming through or water. So if there's anything coming through at all, like oil or water, then he'll probably say, hey, this isn't clean enough. We need to sort out the air supply. You can run the instrument obviously from compressed air from a compressor, or from an air tank, or from a nitrogen tank if you want to run nitrogen. But it does use a fair amount of air. It uses about 10 liters per minute, 10 to 15 liters per minute. So an air tank may only last you a couple of days, a few days. So it's good probably to get a compressor set up and have it clean and dry so that it can be running. Now this whole filter system is really a last resort. It's not got a very large capacity. So if there's a significant amount of oil coming through your airline, it's not going to take long before this gets contaminated, and it would be spent maybe in a week or so. So rather than use up these air filters quickly, it's probably better to make sure that the air coming in is fairly clean. But you should check before you turn on the airline that this is empty, because you'll find maybe that over time you do get a little bit of water in here. And if so, then you should probably turn off the air supply by turning this handle on the top and going and seeing the maintenance people, because the air supply shouldn't have moisture in it. The airline actually is teed off at 2 points, so we have a 5 bar off at for air bearing cooling, which comes on now and again, and then we have motor at 3 bar. Yes, this is the air bearing. Sorry, motor cooling is at 5 bar, and the air bearing runs at 3 bar. So when you first start the software up, it will ask you, you'll first need to set the temperature. So you'll decide, I want to run at 30 degrees or 25 degrees C. And the way you do this is by clicking on the set temperature button. And then this box will open up and you can just type in a set point and hit next, and it will run the test to set the temperature. Now, if you just shut this down, it continues to go to the set point, and you'll see at the bottom of the screen the temperature coming in. So you don't have to watch it do this. You can just set it and then close the test, and it will continue to go to the set point. So you attach a measuring system onto the head. So you do that here by pushing the geometry up into the chuck. It's very easy, and it just clips right in. So as you push in, this ring will clip down over the top, and the RFID chip will recognize the geometry, and that would then prompt you to zero the gap. So you'd make sure the lower plate's in place and that it's all clean and ready to go, and then it should zero the gaps together to start the test, and that would then you'd want to load a sample. So to change out the lower plate, you can slide this lock to the left and then take off the plate, put on the right one, and it either needs to be the same size as the upper or a larger plate is fine as well. And if you want to change out the whole temperature controller, then you rotate this bottom handle 180 degrees and it ejects it, and that disconnects all the power and all the fluids, and then you can take it out and then put in a Peltier cylinder or something like that to use cup and bulb type measuring systems. So these are all plug and play, and they're very easy to use. And when you attach a geometry, it should automatically prompt you to zero the gap. So it's detecting it automatically in the software, and it says, hey, the current geometry is a cone and plate 4 degree 40. If you want to use another one, use it now. So you may have not known what that was. It will actually tell you what it is. If you want to take it out, you just take it out, put the other one in, and then it will say, hey, do you want to zero the gap? And obviously you make sure it's clean and hit next, and then it will come down to zero the gap. Now the force of zeroing is actually 10 newtons, or about 1 kilogram. So if you put your hand underneath, it won't injure you. It might not be very comfortable, but it won't injure you or anything. We do recommend that you don't jam your hand in above the head or anything like that, because I don't think those things have got too much sensitivity, and it may be very, very painful to do that. It should be safe, but I don't think it's going to be very comfortable. So typical rheological testing is that you could use one of these toolkit tests. So on the left-hand side of the screen, you'll see there's a bunch of toolkit tests, and these are the most common sequences. This is your favorites list. Obviously, you can add more to the favorites. You just open any sequence you like and then say add to favorites. So there's the rFind button that we were talking about. You can search on anything. My colleagues typed in the word toolkit, and then it's listing all the toolkit tests. And then you could just click on it and then say add to favorites, and it would add it into this list. But if you added your own in, you could add your own onto the shortcut as well. You can obviously delete these if you don't want to see them, and it will just hide them from the list. It doesn't delete them off the software altogether, it just takes them out of the shortcut list. So these are the default toolkit tests, and you see that there are 5 with a V in front. These are all viscometry tests, and then therefore with 3 with O, that's oscillation, and then 1 which is creep and recovery. So viscometry is for flow behavior, table of shear rates, thixotropy test, maybe 3 steps like low speed, high speed, low speed, a shear stress ramp, we're just ramping through rather than doing a table, a shear rate ramp, single shear rate, and then a shear rate ramp. So you can see these are the most common. And then there's the oscillation amplitude sweep, oscillation frequency sweep, and a single frequency test where you're looking at change of properties with time, and then creep and recovery. So all the toolkit sequences contain rheology information on the initial properties tab. So if you open a sequence rather than just running it, you'll see there's 3 tabs. And on the left-hand side, there's one called properties. And this is just background information about the sequence. So for the viscometry test, it's doing a table of shears. It's showing you it's going to step up in speeds, and it's going to measure the viscosity, which is going to come down to equilibrium at each speed. And it's going to take a point, hopefully, when it's reached equilibrium. And those are going to be plotted on a graph of viscosity versus shear rate. So there's a quick description of what the test will do. And if you scroll down, it tells you what you can change and what version of that test it is. And then if you see, this is another one, Toolkit V002, it's showing you it's a 3-step test, and it kind of explains the background. Now this properties tab is really just text and information, but it doesn't actually do anything. The next tab is the live display. Sorry, go back here. The next tab is the live display. That's how results will be shown when you see them, when it's running. And the last tab is the start sequence. That's what the actions actually do to make it run the test. Okay, so if you want to do a toolkit test, there's an extensive database of tests in here, and not just the ones in the toolkit. So if you said I want to do a shear rate table, you can see there's a bunch of tests that have appeared here. Some of them have models fitting as well. So they're not just the basic toolkit one, although that did come up, but there's actually quite a few others as well. So you can find tests that are pre-written with a test followed by a model fit. So it's worth doing a search to see whether you have what you want before you start designing your own test method. So to open a sequence, you're going to type in the word. You can double click on it and it will run it, or you can right click and then you can actually see the sequence here, and then you can click in the different tabs. So if you click on start sequence, you can see the different actions there ready for it to run. If you right click on it also, then you can see the add to favorites list option comes up, so you can add those sequences into your favorites if you want to. So there's, as I said, there's 3 tabs in the sequence structure. The first one is just the abstract and a bit of info about the test. The second one is what results you'll see and what the tables will look like and things like that. So you can click through the different views, and obviously when the test runs, these are the views that will obviously be there. You can add more even while it's in the middle of a test running if you want to. But it's a nice thing if you can set the test up with the correct views at the start, so that everybody that runs it will automatically see what you want them to see. These axes, by the way, this is eta for viscosity and gamma dot for shear rate. But if you right-click on it, you can say don't use the symbols, and then it will actually show you the whole word. So if you're not so familiar with the rheological terms, you can see the whole word easily. And then the last tab is the start sequence, and this actually shows you what the sequence is doing. So in the test, there's lots of actions, and if you click on one of the actions on the left-hand side in the properties window, you can see what that action's doing. So this is a table of shear rates, and it's showing you that it's going to go from 0.1 reciprocal seconds to 100 reciprocal seconds in 10 steps per decade. So 10 steps per order of magnitude. So in that case, there's going to be 1, 2, 3, 30 steps. Is it 30 points? 0.1 to 1, 1 to 10, and then 10 to 100. So there's going to be 30 points in this flow curve. And if you want there to be less, you could just say 7 points per decade, and it would reduce to 21 points in the test or something like that. Here you can see that there is a prompt for entering the temperature value, and it will ask you to put in the temperature when you run the test, and that will actually overwrite what temperature is in the next action, where it says set full temperature equilibrium. So it will set the temperature to the value that you just typed in. So there's quite a few ways that you can modify sequences. It's very easy, but the 3-step rule is really how easy the software can be. So there's the 3 steps are, if you want to run a sample, firstly you click load sample at the top of the screen here, step 1. Step 2, choose one of the tests in the toolkit. And step 3, click unload. It really doesn't get much simpler than that. Load the sample, run any of the pre-written tests, and then unload the sample, and that will get you data on your result, on your sample, and usually pretty good data because these are very well written sequences. So loading a sample is also stepped you through. So if you click load sample, it says, do you want quick sample loading or full? Now full is actually if you want to preheat the plates and stuff before you load the sample. It takes a little bit longer. If you just say, I want to load the sample and then warm it up, something like that, you can do the quick loading. And then you'll first type in the sample name and any information you want to about it. And then it will prompt you to load the sample, and it will tell you what volume to add. It knows which geometry is on there, and so therefore what the volume should be. And then it will prompt you to trim it off. So if you put too much, you can trim off the excess. If you didn't put enough, you just say no, and it will open up and let you load again. Goes back to this step, goes back to this step again, says trim it. Then when you're happy, you click yes, and then it will ask you to cover it up. So that sequence will run basically through these actions here, and by the time it's finished, you have a sample loaded onto the instrument. Now this isn't the solvent trap cover, this is just a cover for thermal equilibrium, but it does work pretty well if you want to spray some water on the inside and shake off loose drops. That will stop some evaporation as well if you've got a water-based sample. So then running a sequence, we're going to go to the favorites list and click on one of the tests, and then we'll hit start and it will actually go through the sequence. And there's a few buttons at the top here. So there's the start button. If you want to stop it and start it, you can do that as many times as you'd like. You can skip through the actions one by one. If you want to skip through some of the actions, you can click skip. Take a point forces the instrument to take a point if it's taking a long time to reach equilibrium or something. Maybe you started to too lower stresses and the data's all noisy. You just want to step through a bit. You can click point, point, point. Help would bring up the help file, and then obviously close to close the sequence. So this is pretty quick and easy, intuitive. And at the bottom of the screen here, you can see what speed we're at. We're at 0.25 of 31. It tells you how long the test has been running and how long it has left to run. So it's been running for 4 minutes and 3 seconds. We've got 1 minute, 17 seconds left. So after 5 minutes, 20 seconds, we should be done. And this shows you the test is mostly done, just visually. You can see if you want to, by scrolling up and down through this, a list of things that you did in the sequence and what time they happened. And this sequence log will be saved with results. So unloading the sample, just click unload. It will ask you to uncover the covers, and then it will open up the hood, and then it will ask you to wipe it off. And there's a picture of somebody wiping it. And if the sample is really glued on, obviously, then you just eject the top plate and then wipe it off, outside of the instrument somewhere. And then it will ask you if you want to save or save and delete, or just delete the data. So this is pretty easy to use, I've got to say. People usually find it very, very easy to do, and a very user-friendly sample and software testing. So there's actually a lot of data captured with the test, and it will load the sample. It will sample and save all the data from loading, the thermal equilibrium time, and then the test results, obviously, and then you can add analyses in there as well, and you can drag and drop data and merge them on. We can analyze them after the test. So this is our data tree, which occurs on the left-hand side of the screen. So as you progress through the test, it's going to show you how it reached thermal equilibrium. And if this has been expanded, you just click plus, 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 and it blows up the tree here, so you can see every level. And if you double click on the raw data, it would show you a graph of the temperature versus time, so you can see how it reached thermal equilibrium. Or if you right click on any of these steps of the tree, you can send it to a table or a graph, and then you can use the search functions to find which table, or you can create your own table. So you start basically at the top. This would be as the sample's loaded, and then the next test and the next test. So if you did multiple tests on the same sample, these will be sequentially, and you can see everything in there. This is how you'd send the data to a chart. So you click on, say, Final Results, right click, and then say send it to RFinder, and then you can find the right the right graph. So maybe you choose one of the graphs, and it will send it to the right graph, or send it to a table, or you can say open a template that you previously used, or you can change the template if you want to as well. So it takes a little bit of playing with, and I wouldn't be afraid of it. You're not going to break anything. There's also a simulation mode. So when you first install the software, if you go to your start menu on the PC down the bottom left and list your programs, you will find that there are two versions of the software. One is the active version, which is going to try to communicate with the instrument, and the second version is a simulated one, and that actually pretends there's an instrument there, and you can test run sequences and acquire some fake data if you want to. So this basically lets you do a dry run on a sequence to see if it's working correctly, and it's giving you the kind of results that you want. So that's a good option to have too. So what we did here is we looked at the design of the RSpace software and the different types of sequences, and we looked at how the RFinder works, and zeroing and loading the sample, and then running the toolkit tests, and the RSpace capturing data cradle to grave, and showing you how to view the data after a test. Thank you very much for your attention. We're going to go into the second presentation now. So this is module 3, and so we're going to speak about viscosity flow curves, part A and then part B. So how would you make a viscometry test actually on the instrument? My name is Philip Rolfe. I'm one of the technical specialists from NETZSCH in America, and be happy to help you if you need any help with an instrument. So we have two parts here. Part A is an introduction to viscometry, viscosity measurements, and viscosity flow curves. And some of this will be a recap if you've seen any of the previous presentations on introduction to rheology. And then we have different types. We have a yield stress test and then a thixotropy test in part B. So if you remember back, there are two different types of rheology tests. There's the deformation and the flow type. And this would be specifically falling into the flow type. So viscometry testing is when you're shearing a sample round and around to simulate maybe pumping or steady flow behavior, and that's called viscometry. So viscosity is defined as the resistance to flow. Obviously, a high viscosity sample is something very thick, and a low viscosity sample is something very runny or fluid. And we can run most types of sample with the instrument if we use the right geometry, down to even lower viscosities than water, maybe 0.5 centipoise or something like that. That would be about the lowest you could go, or up as stiff as maybe glass or hardened steel. So you'd use a torsional fixture for those things, and you do a DMA type test on the instrument. But for viscometry, obviously you need something that can flow. So you'd be limited maybe to something as stiff as maybe Play-Doh or silly putty, asphalt, also if you do a very slow test. But generally, if you go to really, really hard test samples, then you do an oscillatory testing, because the sample won't stay under the plates or in between the geometries. It would tend to ball up and come out. It just doesn't like to flow. And so we wouldn't do viscosity usually on something that's so solid. So we're going to apply a constant shear rate and measure the shear stress, but also you can use the instrument in stress control mode, so we can apply a rotational stress, a force, and then we can measure the deformation rate, so that it gives you the shear rate. And then the viscosity is the shear stress divided by the shear rate. So that's how you calculate it. Now, there's obviously a lot of different shear rates for different processes. We've talked about shear rate by definition in a previous module, but what are common shear rates? So sedimentation is an incredibly low shear rate. We're talking 10 to the minus 6 up to 10 to the minus 4 reciprocal seconds here. And then maybe leveling after you painted something, that could be 10 to the minus 2 to 10 to the minus 1 reciprocal seconds, or pumping could be 1 to 1,000. Blade coating, obviously quite high shear rates as that sample goes between the blade and the substrate. Spraying could even be up to 100,000 reciprocal seconds. Now this would be the limit really of a Kinexus rheometer. And if you want to go over 100,000, then you'd be looking at a Rosand capillary rheometer, where you can generate up to 1 million or even over 1 million reciprocal seconds, because the sample has to go through the die, and so you can squirt it quite hard there to simulate inkjet printing or reverse gravure coating and stuff like that. So you may have seen this example before, but I'll show you again, because this actually ties into some later examples in this presentation. So there's several situations where the material might see lots of different shear rates. So for instance, a hand cream in its life, if it's flowing at all during storage, it would be a very slow flow rate. Hopefully it will be stable and it won't be flowing. But if it is phase separating or sedimenting, that would be at a very low shear rate, so maybe 0.001 reciprocal seconds. And obviously the more stable it is, the less it's going to sediment or phase separate here. So that would show that the viscosity is sufficiently high in storage. And then we're going to pump it out of that bottle. That would be about 10 reciprocal seconds. And you could see here the pumpability, whether it's a low viscosity there or high viscosity. And then there's that moment that you see that sample on your hand. Does it drip off or does it stay put? And that might give you an idea of the aesthetics of the material. And then in this case, you're going to rub it in, right? So it's going to see, how does it feel? Is it sticky? Does it flow easily? How does it rub into your skin? So this would be the life of a hand cream, if you like. And so we can see these things all with a viscosity flow curve. And materials often fall into 3 different categories. So you've got Newtonian. This is where the material's viscosity doesn't change much with different shear rates. So silicon oil or low concentration dispersions, think of milk or any drink really would probably be Newtonian, more or less. And then shear thinning things like paint or yogurt or polymer and binder dispersions might be quite viscous, and then when you shear them up, they become low viscosity. And occasionally you get shear thickening. This is where the material is quite highly loaded, usually with solids, and when you shear it, it actually gets thicker, and that's because there's not enough liquid in there to lubricate between the particles. And when you displace them from best packing, the interstitial volume isn't easily filled by that liquid. Okay, so having a look at our two flow curve types here, we have one with a yield stress, and so when you go to low shear rates, the viscosity seems to go up and up and up and up, almost just to be solid. So it doesn't flow. This material doesn't really seem to flow, but it's more solid-like when it's at rest. And we say it has a yield stress. Now, it may actually have a very high plateau, and it does flow over a period of months or years, but effectively, you know, it's not flowing when you look at it over a short period of time. And so we'd say it has a yield stress or an apparent yield stress. And then other materials, so this could be your hand cream, you see. So if you open that jar of hand cream, then you can still see the surface profile from when you last scooped some, that would indicate that it's solid-like at rest and it hasn't leveled out. So the fact that you can open that jar and still see some fingerprints on it, or these finger push marks where you pushed it around, shows that it has a yield stress. Now, if you open a jar of honey, you'll see that it's usually very smooth, and that's because honey has a 0 shear viscosity, and that's a plateau of viscosity at the low shear rate. So it has a liquid-like behavior when stationary rather than a solid-like behavior. And you can see here from the low shear rate that you're looking at the weak interactions in the sample. As you go up to these very high shear rates, you're going to see more of the stronger interactions. You're going to break down the weak ones, and the viscosity hence drops. And then you can see, do these stronger interactions break down as well? It continues to drop in viscosity, or is it plateau out? So this gives you an idea of usually the solids loading. Is it very highly loaded or not? This would show you if there's any electrostatic forces in the sample that might give it viscosity at the low shear rate end. So how to test a sample is that you would choose the viscosity flow curve, table of shear rates maybe here. And if you can't see these, you can type in the word toolkit in RFinder, and it will list you a bunch of tests. And then we can load our sample as we discussed earlier. And then we would see the sequence. You can edit if you want to, or you can hit start. So that's this little green arrow on the right here. And it will prompt you to enter some start and end shear rates. Now it will have default values. There's 0.1 to 110 steps per decade. So it's going to be 30 points on the flow curve. You can obviously change that. If you want to simulate pumping, you might say 1 to 1,000. Or if you want to look at sedimentation, you could put 10 to the minus 2 to 10 to the minus 1, or 10 to the minus 3 to 10 to the minus 1, or something like that. And then it will generate the flow curve for you. So this is automatic. And if you really want to mess with the test, you need to open it and then change the parameters in there. But the default test methods should work pretty well. You can see here viscosity flow curve for the hand cream in blue. And you can see at low shear rates, it actually does have a yield stress. You see the viscosity seems to go up and up and up indefinitely, indicating it's got solid-like behavior. And then this is a shower gel, which behaves more like a honey. And actually, this would level out in the bottle. So interestingly, when you pump the material, they become almost the same viscosity. So you wouldn't be able to see the difference between these using a low-cost viscometer, but obviously you can with a Rheometer system. So in summary, with this section, we've looked at introduction to viscometry measurements. We looked at mimicking processes with the Rheometer. Obviously, you need to look at your process and see what shear rates may be applicable, and then use those shear rates in your test. And there's 3 different types of tests. There's the flow curve, and then next we'll go into the yield stress and the thixotropy test. So thank you very much for your attention, and this is the end of part A of module 3. This is part B of module 3, and we're going to discuss now the other viscometry measurements in yield stress and thixotropy. My name's Philip Rolfe. I'm one of the rheology technical specialists here in the USA at NETZSCH, and I'll be happy to try to help you if you need any help with your testing. So one of the test methods we looked at was viscometry, that's just steady shear flow. Another test method is yield stress. Now this is the resistance to flow. So when you first look at some samples, if you think of butter or toothpaste or ketchup, it may seem like it actually isn't flowing initially, and you need to exert more than a certain amount of force onto it to get it started. So the yield stress is why you need to squeeze hard enough on the tube, which is why you need to whack your bottle of ketchup to get some of it out. Or when you have a pump, maybe the material doesn't flow initially. There's a startup time or startup pressure. It needs to exceed a certain pressure before the material starts flowing in that tube. And so we can measure these things with a stress ramp. It's actually quite a useful thing for a rheometer to do this. And you can't do this with a low-cost viscometer usually because they're rate controlled. But if you have a stress controlled instrument where you're increasing the force or the stress, rotational stress with time, then you can apply more and more rotational stress and see when the sample starts to flow. Now, if you looked at speed, it would be 0, and then suddenly it would come away from the axis. And so if you plotted rate here, it would be as you ramp up, there'd be no flow and then suddenly moves away. There's with rate here and stress on the x-axis or y-axis. But we normally use viscosity versus shear stress. And initially, when you stress a sample, it pulls back. So you stretch it a little bit and it seems to be pulling back on you, and you pull a bit harder and the sample pulls back a bit harder. It's not initially flowing, so you just get some stretching behavior and the viscosity appears to be going up. Now this is only because we're looking at instantaneous viscosity, and so it's not really going up in viscosity, it's just not flowing yet. And then you reach a point when you pull hard enough and it just starts to flow, and then it will start to break down and go into viscous flow behavior. So if we look at this viscosity versus shear stress curve, you'll have elastic behavior, the yield point, and then viscous flow. And so you can find here from this result very quickly where did it peak, and the peak of this will show you the yield stress of the sample. So this is a great quick test. It just takes a couple of minutes to run, and it can show you a lot of useful information. How's this yogurt going to have in your mouthfeel, you know, for instance, is related to the yield stress. There's a sample here shown in a dotted line. This has no yield stress, or at least nothing that we measured. Maybe if you went to very low stress, you could see it had a yield point back here on the left, but we can see that it doesn't have any particularly big yield stress in this case. Now, if the sample's results come out more or less flat, that would just show it's a viscous liquid. If they're very sharp here, this would show it's more of a brittle gel. So the shape of the curve, or how rounded it is or sharp it is, indicates whether it's viscous or viscoelastic, or if it's very elastic when it just goes up and then straight down again, that would be very elastic. So here's some example results. So we go to the Toolkit V003 and we run that and it will ask you to enter your stress range, and you need to kind of guess what the yield stress is, or if not, you just put in a wide range of stresses which you think will start below and end above the yield stress of the sample. And a good rule of thumb here is the yield stress of ranch salad dressing is about 10 pascals, and toothpaste is about 200 pascals. So if you think, is it thicker than ranch, is it thicker than toothpaste, you can get an idea. So let's You only have to be in kind of the right order of magnitude here. But if you have a low viscosity material, let's say you were testing hummus, I would guess maybe hummus is a bit thicker than ranch. So I'd guess maybe if ranch is 10 pascals, hummus might be 50 or 100. So I could go from 0 to 200, and we're giving it 1 minute 40 seconds, and it's going to ramp up from one stress to the other. And then we should see initially the viscosity going up and then going down, and that would show you where it peaked, and that's the yield stress point. So here's some example results from the hand cream. You see the hand cream in this case had a fairly low viscosity. It must be a fairly soft hand cream. So it is about 5 pascals of yield stress, whereas the shower gel, very smooth and rounded. As you can see, it's not really elastic at all. In this case, it's just a viscous flowing liquid. So this shower gel, I'd imagine if you tip this bottle up, it will just flow. And you can see it's fairly smooth there, you see, so that indicates that it doesn't really have a yield stress either. Okay, the second test that we might use with rheology in viscometry mode is thixotropy testing. And you do this a lot when you want to see the time dependence of a sample. So if you think of some materials, they're not just shear thinning, they actually also are time dependent. So if you have shear thinning behavior, but it takes time to recover after thinning, then you'd call it thixotropic. So this would be, imagine yogurt, for instance. If you take a yogurt from the fridge and you take the lid off, initially it's got some kind of a gel structure. You stir it up with a spoon, it becomes a low viscosity liquid. And then if you wait long enough, if you put it back in the fridge and waited and took it out the next day, it would probably have become a gel again. So it takes a long time to rebuild that gel structure, but it does actually rebuild it. And so it's a thixotropic liquid. So here's a paint. We are going to take it from the shelf, and we see it's somewhat gel-like. We're sharing it here with a mixing blade with a drill gun, and now it's a low viscosity liquid, and we can paint it. Now, the rebuild time for some materials, like paint, is quite a key parameter of how it's going to behave. So you think about this: if you paint on the wall and it rebuilds too quickly, maybe it's going to leave you brush marks, especially if you sprayed a car or something with a rattle can. Then that spray paint needs to level out, right? So a good paint in this case would rebuild a bit more slowly, and that would level out, leaving a smooth finish. But if it rebuilds too quickly, you might get the orange peel effect or brush marks, you know, if you're using a brush. So the rebuild time is critical. If it rebuilds really, really slowly, not shown here, then maybe it would run. So you've got a kind of too fast a rebuild, too slow a rebuild, and then there's the ideal somewhere in the middle. So what we do in this test, we'll do a low shear rate initially, and this will just show you the initial viscosity as a kind of a benchmark. So a very low shear rate, the sample is quite viscous, and then we're going to give it some high shear rate to simulate brushing or mixing or what have you, and the sample is going to break down in viscosity, and then we're going to go back to a low shear rate again, and you can watch the rebuild time. So this is the 3 steps sequentially, and so we call this a 3-step test. So it's going to ask you when you set up the test, what do you want for step 1, do you want step for 2, and what do you want for step 3? Obviously you can change these as you like, but there's some good defaults in there. I think it's probably 0.1, 100, and 0.1 again, and the third phase is 10 minutes long, and there's a point every 2 seconds there. So you can see the data here. We have the high viscosity, low viscosity, and then a rebuilding viscosity. Now, this is another result, and it's actually plotting the shear rate here in blue. So you can see the low speed step, the high speed step, and the low speed step. And this was a pharmaceutical product. It's a calcium carbonate suspension for indigestion. And I think it tells you you have to shake before drinking in this case. So this person would shake it up, and that would be like the high shear, and the viscosity is obviously coming down a bit during that shaking process, but it rebuilds fairly quickly. And you can see here we're back up to the start viscosity in maybe 100 seconds or so from this point. So I'd say from about 80 seconds to 180, it would have recovered most of its structure. So pretty interesting to see how the material breaks down during shearing and how quickly it recovers. Very, very good comprehensive data, and it really helps a formulator know the effect of different additives in his dispersion. So the longer it takes to rebuild, you can say the more thixotropic it is. And also it might show you how long it takes to get to steady flow in a flow curve, if it takes a long time to break down, or if it takes a long time to rebuild. And so it's quite important to know this if you want reproducible measurements. So let's say, for instance, that I took a sample out of the cupboard and I mix it and test it, then I'm going to get a lower viscosity result than if somebody else takes that yogurt, for instance, out of the fridge and they don't mix it, they just load it straight on the instrument, then they might get a higher result. So we'd have to say, hey, let's always mix our samples in this case and then give it so many minutes to recover, and then we'll get reproducible measurements. But you need to understand, hey, this is a thixotropic sample, so we need to pre-shear it and let it rebuild for a certain time, which you can have automatically done with the test. Or maybe you say we won't pre-shear it at all, we'll always load it very carefully or whatever. So in summary, thank you for your attention. We looked at yield stress, which is the force required to start a material from flowing. And then we looked at the thixotropy, which is the rebuild time of the sample after a shearing process. And it can show you something about the time dependence of that material's viscosity. Thank you for your attention again. And if you have any questions, please don't hesitate to call me. My name's Philip Rolfe, and it's philip.rolfe@NETZSCH.com. Thank you.